Time to begin. How's everyone doing? Doing good, hopefully. Today we're going to be talking about infinite limits. I'm going to start off with the very last little bit that I didn't get to yesterday. The intermediate value theorem. The intermediate value theorem is important, but I don't think I'm going to make you use it a whole lot. But yeah, before we start with anything, I've got some announcements. Homework is due Monday. Hello. So I'm gonna get the homework that was due this Monday graded over the weekend. Okay, get you some feedback on that. This is a reminder that I'm gonna be out of town Wednesday through Friday next week. So class is gonna be virtual for everybody on Thursday and Friday, and I'm gonna be having virtual office hours on Wednesday, office hours on Friday. I don't think I'll hold. I'll let you know if that changes. But definitely Wednesday, I'm having virtual office hours. Thursday and Friday, class is going to be completely online for everybody. Okay. So, and then office hours I have today are from 1 to 3 in the PM. Stop by if you want to talk about calculus and problems or math in general. Math is great. You all should all be math majors, by the way, because it's so much fun. All you need is a paper and pencil. You don't need any experimental stuff. Get out of here. All right. Are there any questions about this before we get started?
No, you could say that about English.
Yeah, but this is math, though. I do. My wife is. She majored in creative writing and graphic design, and so I'm not gonna ever talk smack about English majors or anything like that. I also think that's very important, but math is a little importanter, you know.
That also be said for psychology majors.
I'm not gonna talk smack about any of the math is the most important. That's all I'm gonna say. Okay. All right. So. Okay, so let's talk a little bit about the intermediate value theorem. Intuitively, this is a theorem that once I draw the graph, you're going to say, yeah, that makes a lot of sense. To actually prove it is actually a kind of a difficult proof to look at. And so if anyone's ever a math major, it's a fun little puzzle to work with to prove this seemingly obvious thing. But last time I didn't cover this. This theorem says that if f of x is a continuous function on the closed interval a to b. So that meant, remember, continuous on the open interval a to b means that the limit as x approaches c of f of x equals f of c for every c between a and b. And then continuous on the closed interval a to b also means you have these two extra conditions. You have that the limit as x approaches the left endpoint from the right, so a from the right of f of x is equal to f of a. And then the other condition was that the limit as x approaches the right endpoint from the left, so approaches b from the left of f of x is f of b. Okay, so that's what continuous on the closed interval a to b means. So if f satisfies these conditions, then f of x has to hit every single value between f of a and f of b. It has to attain every value between f of a and f of b. And to just say that, it's a little abstract. So I'm going to draw something for you. I'm going to draw a general intermediate value theorem problem. Oh. Okay, so let's say a for us is -3. So we're looking at the closed interval, -3 to, I don't know, 2. So this right here, -2.5 roughly, is this is f of a, right? Because a is -3 and b for us is 2. And then f of b is up here. And these could be switched, obviously. It could have, f of a could have been up higher than f of b. That's also fine. But all the intermediate value theorem is saying is that f of a has to hit every single value between, f of x has to hit every single value between f of a and f of b. Okay. So, check. Did I write the wrong thing back here? The limit as, oh, yes, you're right. It should have been a plus. Thank you. Limit as x approaches a from the right. I said the right thing, wrote the wrong thing. So the idea is that f has to attain every single value between here, between the two blue circled points. So let's say the number 1 is between f of a and f of b, right? F of a is -2.5. F of b is 4. So that f has to, at some point, for some x value between -3 and 2, it has to go through the y value 1. Okay? There's no way, if I'm drawing from here to here without lifting my pencil, I could try to avoid it, but eventually, if I want this to be a continuous function, I have to go through the line y equals 1, right? Does that make sense? That's all the intermediate value theorem is saying. There's no way, if you have a continuous function, there's no way to jump over a point between two function values. Okay? So the way this is typically, one application of this is that if a function is positive at some point, so let's say this function is positive at x equals -2 and negative at x equals, I don't know, 3, then what has to be true about the function that is positive here, and negative here? Well, if it's positive at one point and negative at another point, it had to go through 0, right? It has to cross the x-axis to go from positive values to negative values, yes? So again, no matter if this function is continuous, no matter how I draw it, and it can go outside of the interval too, it can do something like this. But no matter how hard I try to, I can't avoid going through 0 to get to that negative value from a positive value continuously. Okay? Any questions on this? Okay, like I said, this theorem is important in like later math classes. I'm not going to test you too much on it, other than maybe asking you a question like, if a function is positive at one point and negative at another point, and it's continuous, then does it cross the x-axis? And the answer is yes, it has to. Okay, so that is that. All right, so now we're going to talk about infinite limits, if nobody has questions about the intermediate value theorem. Okay, here we go. Infinite limits. So yesterday I sort of said, you know, these asymptote discontinuities, that's something I'm going to test you on, and then I sort of ignored it for the rest of the class. Today we're going to talk about the asymptote singular or discontinuities, right? So I'm going to start off with a technical epsilon delta definition of a infinite limit. And really, there's no epsilon going on here. Really, this should be an m. It's really we actually, instead of wanting a really small number, if things are blowing up, we're going to take a really big number that I'm going to call m instead of epsilon, so I don't confuse everybody. Okay, so there's the technical definition for a statement like the limit as x approaches a of f of x is positive infinity, means that for every m bigger than 0, and these m's, so before this was an epsilon, for every epsilon greater than 0. Now this is an m, and m I'm thinking is a really big number, not a really small number that's close to 0. M is getting bigger and bigger and bigger. So for every big m bigger than 0, there is some delta. So that 0 is strictly less than, I accidentally put less than or equals on the notes that you guys have. It's actually strictly less than. So make sure you cross out the line underneath, because it doesn't, we don't need to have f defined at a. So for every x close to a, right, that's what that statement means, x close to but not equal to a, then you have f of x is bigger than m. Okay. So I'm going to show you on a graph what this means. But if you want to talk about the limit as x approaches a of f of x equals negative infinity, it's the exact same thing. You just take a big m, and then you need to find delta bigger than 0, so that if 0 is less than x minus a in absolute value is less than delta, then f of x has to be less than negative m. Okay. Are there any questions about this technical definition before I show you what it means graphically? All right, so these definitions have almost identical formulations if you're looking at the one-sided limits. And we will be, a lot of the time when we're looking at infinite limits like this, we'll only care about the one-sided limits. Specifically when we're talking about asymptotes. A vertical asymptote isn't just where the limit as x approaches a is infinity, because f could go to positive infinity on one side and negative infinity on the other side. We would still not call that an asymptote. So we're going to work a lot with one-sided limits today, but all these have very similar definitions. All right, and so a word of caution before we move on. This does not mean that a limit exists. If I say the limit as x approaches a of f of x is infinity, that is not me saying that the limit exists. Limits have to be real numbers, finite numbers, okay? It's just a different way of saying that the limit doesn't exist. We're saying sort of exactly how the limit doesn't exist. Because there are a couple of ways for a limit to not exist, right? We could have had the sine of 1 over x type limit where it keeps bouncing back and forth, and we could have jump discontinuities. Limits fail to exist there. This one we're specifically saying how the limit is failing to exist. Okay. All right, so let's show that using this technical definition. This is the last time we're going to use the technical definition. We're going to show that the limit as x approaches 0 of 1 over x squared is equal to infinity. Okay, and so the idea here, I'm just going to draw a graph really quick. If I take m, let me draw it in red. If I take m to be there, so m is the red number, whatever it may be, then I need to take delta smaller than, well, if I just drop this down, there, then delta needs to be that length, right? Because if x is closer than delta to 0, then this function is only staying above that red line, the way it's drawn, right? So that's the idea. Let's actually write out using m's and deltas. So if we're, instead of an epsilon delta proof, we do this as an m deltalon proof. So instead of starting by saying epsilon is bigger than 0, we're going to say let m be bigger than 0. We want to find delta. These problems still work backwards. Start with what you want to end up with. So we want to find delta so that 1 over x squared, if x is close enough, so within delta of 0, we want to find delta so that 1 over x squared is greater than m, right? So we want to find, that's what WTF stands for, want to find delta. Oh, nobody thinks the WTF joke is funny anymore. We want to find delta so that, delta greater than 0, so that 0 is less than x minus a. But what is a for us here with this problem? I'm looking at the limit as x approaches 0. Yeah, perfect. So a is just 0. So I want to find 0 less than x minus 0. So 0 less than absolute value of x less than delta implies this. That's what implies. Okay, well, now I can just solve this inequality for x, right? So what should I do to both sides? Multiplying both by 1? What do you mean? Yeah, if I multiply both sides by 1, I could do that, but that won't change. That won't change much. All right, yeah. If I multiply, yeah, I want to get one side to look like 1, right? So if I multiply both sides by x squared, then I end up with 1 has to be bigger than m times x squared, right? Then what do I want to do? I want to find out what x has to be, right? Or really what delta has to be. So I kind of want to get x by itself in this inequality right here. Yeah, I need to divide by m, right? So I divide by m, I say 1 over m has to be greater than x squared. And then what do we do? Yeah, I take a square root. Perfect. When I take a square root, well, I'm going to get square root of 1 over m. And because I'm introducing the square root, you want to introduce a plus or minus, right? If I ever just write down the square root, if I ask you to find the square root of 4, it's fine for you to just say 2. But if you introduce the square root into a problem, you have to put plus or minus, okay? So plus or minus 1 over m in this, the square root of 1 over m, this is greater than, and then if you take the square root of an absolute value, or of a square, you actually end up with the absolute value of x. Okay. So then, I can't have the negative square root of 1 over m be greater than something that's an absolute value. That's an extraneous solution here. So the only thing I get, I don't care about the negative. So the only thing I get that makes sense is absolute value of x. I need that to be less than the square root of 1 over m. And by definition, I can't plug in 0. So I have that, right? I can't plug in 0 into this function. So then what's delta? Compare this line to this line. What does delta have to be? Perfect, square root of 1 over m. And it makes sense Does that make sense for delta to be a small number? Yeah, because m is really big, right? M is a really big number, so when I take 1 over m, that's going to be really small. Taking the square root will increase it a little bit if m is big enough. But yeah, square root of 1 over m is going to be very small if m is very big. So if we take delta equal to square root of 1 over m, then we can just work backwards now. Start from here and then work backwards to get exactly what we want, right? So, are there any questions about why delta needs to be less than or really equal to square root of 1 over m in this technical m delta group? Okay. All right, so a lot of times we're going to be looking at graphs to determine left and right hand limits of functions that are blowing up. So let's use Desmos. If you have Desmos, let's open up Desmos on your iPads, or there's also a website if people at home, if you don't want to bust out your iPads or whatever. But use Desmos to plot these functions here: x over x squared minus 4x plus 4, and x squared over x, or sorry, x squared over x squared minus 5x plus 6. And I want to know what the left and right hand limits are of these two functions here as x approaches positive 2. Okay. So I will open up Desmos now. Desmos. Cool. So the first function we had was y equals x divided by x squared minus 2x, right? Or minus 4x. And then plus 4. All right, so here is the graph of the first one. And I want to know what the left and right hand limits are as x approaches positive 2. So what does it look like? Here I can zoom out. Yeah, it looks like both the left and right hand limits are positive infinity as x approaches 2. Does everybody see why? It looks like, yeah, it looks like it's blowing up there. If I take x really close to positive 2, then I can make f of x as big as I want by taking x closer and closer and closer to 2. F of x is not defined at 2, right? And that's fine. Yeah, exactly. And this is because we're getting a 0 in the denominator. Okay? And I'm going to mention that here in a minute. That's kind of the key way to point out, to spot where you're getting these asymptotes. Okay, so that was the first one. Let's look at the second one. I'll add a new graph. All right, so second one, y was equal to x squared, x squared divided by x squared, and then can someone tell me what the rest was? Minus 5x?
Minus 5x plus 6.
Thank you. Minus 5x plus 6. Okay, so what's happening with this one?
Something going on at the bottom.
Hmm?
Below the x-axis.
Ah, thank you. All right, home. All right, yeah, let me get rid of this graph now. All right, so yeah, this one, thank you very much, because that could have very much tricked me. So for as x approaches 2 from the right, what does it look like is happening? And 2 is, at this zoom level, 2 is that first tick mark there. So as x approaches 2 from the right, it looks like we're approaching, careful, so that's actually a different value there, I think. As x approaches 2, yeah, as x approaches 2 from the right, we're actually looking at that part of the graph, and we're getting negative infinity. So this is a graph that you need to be careful about. But yeah, as we approach 2 from the right, we're approaching negative infinity. And as we approach 2 from the left, we're approaching, yeah, that one's positive infinity, right? So I do have these plotted. I have these just in here. So here's the first graph. And this one, there's nothing funny going on, no funny business. As we approach 2 from the right, we're blowing up. As we approach 2 from the left, we're blowing up. So in this case, we would say that the limit as x approaches 2 from the right of this was x over x squared minus 4x plus 4. Well, that's equal to, if you want to put plus infinity, that's fine. If you just want to put infinity, that's also fine. And similarly, the limit as x approaches 2 from the left of x over x squared minus 4x plus 4 is equal to plus infinity. And so if you wanted to write the limit as x approaches just 2 overall of x over x squared minus 4x plus 4, you could write that that is also plus infinity. On the next one, we're not going to be able to do that because on one side we're going to positive infinity, on the other side we're going to negative infinity. So yes, let's look at the next one. Very tricky, very, very tricky going on here. But the next one from the right, as we approach 2, the function comes up a little bit, but then it shoots back down, right? So the limit, it looks like the limit as x approaches 2 from the right of x squared over x squared minus 5x plus 6, that's actually equal to negative infinity. And then the limit as x approaches 2 from the left of x squared over x squared minus 5x plus 6, that's equal to positive infinity. And that's all we're going to write for those, okay? Because we can't, because the limit's approaching plus infinity from one side, minus infinity from the other. So you can't write the limit as x approaches 2 overall for this one. If you tried to answer that limit, you would just say does not exist because it's approaching plus infinity from one side, minus infinity from the other. Are there any questions on that? Yeah.
I know this is stupid,
No.
but I'm still missing, like, for the top half,
Mm-hmm.
why couldn't it still be, like, if it's approaching it from the right above the x-axis, why wouldn't that count as positive?
Oh, that part that counts, but that's actually the limit as I maybe should have made these. So let's actually look at the denominator here, because what's happening is the scale is tricking our eyes a little bit. So here, this function is actually x squared over, what is the bottom factor as? Is x minus something, or x plus something, x plus something? Minus 3, minus 2, right? So what's actually happening there as we approach 2 from the right, well, yeah, as you go through 3, that's actually blowing up at x equals 3. And that's a very excellent question. What 3 is actually, in terms of calculus, like really far away from 2. Because when we talk about those deltas, like the deltas that we're talking about are like 0.00001. So what's happening at 3 does not affect the limit as x approaches 2. Okay, so that's yeah, an excellent question. The limit as x approaches 3 from the right here, that's definitely positive infinity. But that doesn't affect the fact that as we get closer and closer to 2 from the right, we get that negative infinity there. Okay. Any questions on that? Any other questions? Okay. So this brings us to vertical asymptotes. This whole time I've said this word asymptote. I said it that these are all asymptote discontinuities, and thankfully no one said, "What's that word asymptote that you're using?" Well, this is what a vertical asymptote is. Okay, the definition of a vertical asymptote is the vertical line x equals a is a vertical asymptote of the function f of x if the limit as x approaches a of f of x is plus or minus infinity from one side or the other, or both. But as long as you have the function is blowing up on at least one side, the function has a vertical asymptote there. So one of the most useful ways to spot vertical asymptotes, as we mentioned before, well, when you have division by zero happening in the denominator, right? And this is all a bunch of language that is all math language to really just say, if you're ever trying to take some function divided by another function, if you're ever looking at the limit where you're dividing continuous functions and the limit at the top of the top as you plug in that number is not zero, and the limit of the bottom as you plug in that number is zero, then you're definitely going to get a vertical asymptote there. Okay. So this is what I was mentioning before. Like when in limits, you can have a factor that is zero at a point as long as there's something to cancel it. That won't give you an asymptote. But here we're saying there's nothing to cancel the zero in the denominator in the numerator. Okay. All right, so find the vertical asymptotes, if any, of the following functions. So we've got f of x is 1 plus x squared over x squared, or sorry, x to the fourth minus x squared. That's pretty small. Let me zoom in a little. F of x is 10 minus x over 4 plus x squared. F of x is 10 minus x over x squared plus x to the fourth. And the last one, f of x is x squared over x squared minus 2x. So all pretty similar looking functions, but we're going to get some totally different behaviors from all of them, right? So let's look at this first function here. I actually have. So first function, f of x is equal to 1 plus x squared divided by x to the fourth minus x squared. All right, so using that last thing that I said, we want to look for spots where, for vertical asymptotes, especially when we have a quotient like this, we want to look for spots where the top is non-zero and the bottom is zero, right? So in order to do that, we're going to be factoring most of the time with these types of problems. So what does the bottom factor as? Well, what do both those terms have in common?
It's x squared
Perfect.
times x plus 1, x minus 1.
Yes, perfect. We get x squared times, really quick, I'll write it as x squared minus 1, but then you're exactly right. Then that is a squared minus b squared, right? So I'm going to leave the top as it is. So this is 1 plus x squared over x, there's a hair on there, over x squared times, well, x squared minus 1 squared, that factors as x minus 1, x plus 1. Okay? So does anything cancel with anything in the top? Be careful. The top is meant to trick you. In case anyone thought that the top factors the same in a similar way as the bottom, it does not. The top. No, if it was just x squared over x squared, but the 1 plus x squared throws that entirely off. I can't cancel those factors because and the top is addition, and the bottom everything's multiplication. I can't cancel that x squared out. So there is no cancellation going on here. There is no cancellation going on here. So we get x equals, well, from that factor, we get x equals 0. From this factor, we get x equals 1. From this factor, we get x equals minus 1. Okay. So these are all vertical asymptotes. Again, there's nothing to cancel these factors in the numerator. And so if you want, you can look at the graph of this. We can look at the actual limit itself. But for right now, what I want you to be able to do is spot vertical asymptotes by setting the denominator equal to 0. All right, so let's look at the next. Well, actually, let's actually look at one of these limits. Let's look at the limit as x approaches 0. Just say from the left of this guy, 1 plus x squared over x squared. I'm going to leave it factored. X squared, x minus 1, x plus 1. All right, we could look at the graph, but I'm going to show you another method where if you know something's blowing up, a quick little method to decide whether it's going to plus infinity or minus infinity. Okay, so what sign as x approaches 0 from the left? First of all, that means x is very small and negative, right? So when I square a very small negative number, do I get a positive or do I get a negative? I get a positive, right? So I'm looking at something that looks like positive down here for very, very small x not equal to 0. So this is still the limit. Okay, what about this factor? If x is very small and negative, then what sign does x minus 1 have? It's negative, right? Think of just like x equals 0.1 or negative 0.1. Well, x minus 1 is going to be negative 1.1, right? So this one's also going to be, or it's going to be negative. And then what about this factor here? Well, if x is very small and negative, then 1 plus x, is that going to be positive or negative? So just take x to be, say, like negative 0.1. What's, yeah, positive, exactly. So we're going to get positive here. And then the top, 1 plus x squared, what sign does that have? It's positive, right? It's going to be x squared is positive no matter what. And then I add 1. Well, that can only make it more positive, right? So I'm going to have positive up top. So looking at this, I'm going to have a positive divided by positive times negative times positive. So overall, what's the sign of this going to be overall?
Positive.
Careful, I've got positive, and then divided by positive times positive. I'm going to get a negative in the bottom, right? And so positive divided by negative, that's actually going to give me a negative. And so what do we think is going to happen then as x goes to 0 from the left? Are we going to get positive infinity or are we going to get negative infinity? Yeah, we're going to get negative infinity. These values are all, for x close enough to 0 from the left, these values are going to all be negative just from examining the signs here like this. And so f of x has to go to negative infinity. There's no way it can go to positive infinity through negative values. Okay? So you can do that with all the other one-sided limits and come to similar results about plus or minus infinity. Okay? So this is actually going to give me, going to erase. So this is actually going to give me here negative infinity. I'm just going to write limit as x goes to 0 from the left of f of x is negative infinity. All right, so let's look at the next one. The next one, who can, someone read it off to me. F of x was 10 minus x over 4 plus, oops, 4 plus x squared. Thank you. The limit as x, oh, I'm just finding asymptotes, sorry. So f of x equals this. So where does this function have any asymptotes? Or does it have any asymptotes?
No, they're imaginary.
Perfect. Yeah, yeah. Whoa, imaginary numbers. Whoa, whoa. Yeah, so instead of talking about imaginary numbers, which I'm very glad that you know about, I'm just going to say, well, the bottom x squared is always bigger than or equal to 0, right? Take any real number and square it, and you get something that is positive or 0 if you squared 0. Okay, so this is bigger than or equal to 0. So then 4 plus x squared, well, that's got to be bigger than or equal to 4, right? So 4 plus x squared has to be, it's never equal to 0, right? If you tried to solve for 4 plus x squared equals 0, then you were exactly right. We get x squared equals negative 4, but then that statement doesn't make sense for real numbers. I can't square something and get a negative number. Okay, so no asymptotes. Asymptotes. Okay, that's how asymptotes is spelled, by the way. I-S-Y-M-P-T-O-T-E-S. Okay, any questions on that one? All right, can someone read me the next one? F of x is 10 minus x over x squared plus x to the 4th. All right, so again, these rational functions, or anytime I'm dividing two continuous functions to find the asymptotes, I just set the bottom equal to 0 and make sure nothing cancels, right? So this is equal to, really quick, 10 minus x. What does the bottom factor as?
X squared is 1 plus x squared.
Perfect. X squared times 1 plus x squared. So if I set the bottom equal to 0, x squared times 1 plus x squared equals 0, well, then either x squared is 0, right? But if x squared is 0, what does that tell me? That x is 0, right? Or 1 plus x squared is 0, right? What does that tell me? Or does it tell me anything? If you tried to solve 1 plus x squared equals 0, yeah, then I get x squared equals negative 1. And does that make sense? No. So the only asymptote we get here is x equals 0 because there's nothing in the top to cancel it. All right. One more of these. All right, that last function was x squared over x squared minus 2x. So last one, x squared over x squared minus 2x. Okay, well, again, what is the bottom? We need to always factor the bottom. So what is the bottom factor as? What? X parentheses x minus 2. Perfect. All right, and so you want 0 and 2 if we're yeah. So the bottom is equal to 0 when x is 0 or x is 2. But careful, what happens you should always simplify as far as you can go first. So what can I do? I've got x squared up top. That's x times x, right? So I can cancel that x with that x. I gotcha. So this function really is x over x minus 2 in disguise, right? And so what's the only asymptote? X equals 2. Very good. Very, very good. So always make sure to simplify as far as you can go at every step. Okay. Any questions from anybody before we move on? Anybody online, any questions? Wonderful. All right, here we go. So properties of infinite limits. So the properties of infinite limits, you need to be a little bit careful. These are going to look kind of like those tables I've shown you before with continuous limits, but you need to be careful. So if you're adding, so first of all, here I'm assuming that the limit as x approaches a of f of x is positive infinity, and that the limit as x approaches a for g of x is some finite number L, okay? So if you have this situation where you're adding these two functions where one is blowing up and the other is staying finite, and you're looking at the limit, then you get infinity there, okay? If you're multiplying these two functions, if you're multiplying f, which is blowing up as x approaches a, and g, which is staying finite as x approaches a, then the limit as x approaches a of the product is also blowing up. F is sort of taking over there. Okay. That's if L is greater than 0. If L is less than 0, you just get negative infinity, but it's the same idea. F is taking over, L is contributing the sign. Or G is contributing the sign. Okay, so that's with a product. And then a quotient. So if you divide something that is staying finite, g of x, by something that is blowing up, f of x, if you divide those two and take the limit as x approaches a, then you'll end up with 0. And the idea is f is getting so big and L is staying constant that that forces that limit down to 0. Kind of like the squeeze theorem, but not quite. Okay, so if f is negative infinity and or we're looking at the one-sided limits, all of these still roughly hold. You have to make a few small tweaks. If f is negative infinity, you switch all the signs and everything. But the main takeaway here is just be careful when you're working with two limits where one is blowing up, the other isn't. Sometimes that can work in a very weird way if you're not careful. All right, so let's use this here. So find the limit as x approaches 1 of 4 plus x over x minus 1 squared. All right, so looking back, this kind of looks like this situation, right? Where really g of x here, g of x is 4, and f of x is this guy, right? So I'm looking at the limit as x approaches 1 of 4. Well, that's just 4, right? So that tells us L in that previous slide, L is 4. Now I need to look at what is the limit as x approaches 1 of x over x minus 1 squared. Well, we can graph it, or we can use that trick that I talked about before. As x approaches 1, either from the left or the right, what sign does the top have? The top's going to be very, very close to 1, right? So it's going to be positive, right? It's going to be positive. The bottom, I'm squaring something. So what sign does the bottom have for any number other than 1? Yeah, it also has to be positive. So as I approach 1, I'm taking a positive divided by a positive. That has to be positive. So the limit here of x over x minus 1 squared as x approaches 1 is what? Yeah, it's positive infinity. So it's going to be positive infinity. So then what's the limit? Looking back, that was good for it. What's the limit as x approaches 1? Well, we have this situation. The limit as x approaches 1 of f of x for us is positive infinity. L here is 4 for us. And so we're going to get positive infinity, right? Are there any questions on that? All right, cool. So I think last we just have a little bit of a summary. We're out of time though, so if you want to look at a summary, feel free to look at it on your slides. But does anybody have any questions before we head out? Anybody online? Troy, Madison, any questions? All right, cool. All right, if nobody has any questions, feel free to head out. Please wipe down your desks as you go. If you do have questions that you don't want to ask, come to my office hours. Thanks, everybody.
Thank you.